Have a look at this figure skater. She can glide across the ice in a perfectly straight line. We call that translation. Or she can spin right on the spot, and that's rotation. Now, they're both motion for sure, but they're actually governed by totally different sets of physical rules. So what's really the difference between moving and spinning?
Well, let's dive into the physics of that spin. In this explainer, we're going to break down the science of rotation from the ground up. You're going to see how everything, from a spinning top to the planet Earth itself, follows the same really elegant set of principles.
So here's our game plan. We're going to start with the absolute basics, the language of spin. Then we'll see what happens when things spin up at a constant rate. After that, we'll tackle rotational inertia, which is kind of like mass but for spinning. Then comes torque, the rotational version of force, and finally, we'll look at it all through the lens of work and energy. We're going to build this up block by block.
All right, let's get into block 1, the variables of rotation. Before we can start using the equations, we've got to learn the lingo.
If you're tracking something moving in a straight line, use this position x. Simple. For something that's spinning, we use its angular position, which we write with the Greek letter theta. It's really just the angle of some line we draw on the object compared to a fixed 0 point. And here's a pro tip. While you might be used to degrees, in physics we pretty much always use a unit called radians. It just makes the math way cleaner down the road, trust me.
Okay, so what's next? Well, how far did it turn? That's angular displacement, or delta theta. It's just the change in its angular position from one moment to the next. Now, by convention, we say counterclockwise rotation is positive and clockwise is negative. A great way to remember this? Just think, clocks are negative.
But how fast is it spinning? That's where angular velocity comes in. We use the Greek letter omega for this one. Just like linear velocity v tells you how fast your position is changing, angular velocity tells you how fast your angle is changing. That little d theta dt you see in the formula? That's just the calculus way of saying the instantaneous rate of change. We measure it in radians per second.
And what if that spin is speeding up or slowing down? Well, then it has an angular acceleration, which we call alpha. And you guessed it, it's the rate of change of the angular velocity. That's what d omega over dt is telling us. And boom, there you have it. The 3 big variables for describing any kind of rotation: angular position, angular velocity, and angular acceleration. They're perfect mirrors of their straight-line cousins.
So you might be thinking, hey, position, velocity, acceleration, those are vectors, right? And you'd be mostly right. Angular velocity and angular acceleration, yep, they're vectors. But here's where it gets a little weird, and it's a super important point. Large angular displacements are not vectors. So why not?
This little experiment with a book shows it perfectly. You can try this right now. If we rotate it 90 degrees around the x-axis first, and then 90 degrees around the y-axis, its spine ends up pointing up. But watch this. If we do it in the opposite order, y-axis first, then x-axis, the spine ends up horizontal. For a quantity to be a true vector, the order you add them in can't change the final result. But here, the order totally matters. That's why big rotations aren't vectors. It's one of those cool, counterintuitive things about how the world works.
All right, so now that we've got the basic vocabulary down, we can start putting some sentences together. Let's move to block 2, where we'll check out the rules of motion when something is spinning up or down at a nice, steady rate.
Okay, this slide is just beautiful. It shows one of the most elegant parallels in all of physics. On the left, you've got the standard equations for linear motion that you probably remember. And on the right, the rotational twins. Just look at them. The structure is identical. The physics is the same. All you have to do is swap x for theta, v for omega, and a for alpha. If you get one set, you already get the other. It's an amazing shortcut.
Okay, on to block 3, rotational inertia. We know that mass is an object's resistance to being pushed. It's stubbornness, right? So what's the rotational version of that? What's an object's resistance to being spun?
That property is called rotational inertia, and we use a capital I. Now, the huge insight here is that it's not just about how much stuff there is, it's about where that stuff is. The formula tells us everything. You have to sum up every little piece of mass multiplied by the square of its distance from the axis. That r squared is a massive deal. It means that mass far away from the center contributes way more to the inertia than mass that's tucked in close.
And this slide gives you a perfect gut feeling for it. Imagine trying to spin this rod. On the left, we're spinning it along its length, like a drill bit. All the mass is super close to the axis, so it's really easy to get it going. It has a low rotational inertia. But on the right, when you try to spin it like a baton, whoa, all that mass on the ends is far from the center, and it really fights you.
It's much harder to spin because its rotational inertia is way higher. Same rod, same mass, completely different result.
Now, calculating rotational inertia for weird shapes can get really complicated. Luckily, physicists have this amazing tool called the parallel axis theorem. The formula is I equals ICOM plus mh squared. Basically what it says is, if you know the rotational inertia through an object's center of mass, that's the ICOM part, you can easily figure out the inertia around any other parallel axis. You just have to add on a term for the total mass m times the squared distance h you move the axis. It's a hugely useful theorem that saves a ton of work.
So we've got the rotational version of mass. The next obvious question for block 4 is, what's the rotational version of force? What's the twist that actually causes something to start spinning in the first place?
That twist is called torque, and we use the Greek letter tau. The best way to get it is to just think about opening a heavy door. You push on the handle, right, as far from the hinges as possible, and you push perpendicular to the door. You do all this without thinking, because you intuitively know that the twisting effect, the torque, depends on how hard you push, how far from the pivot you push, and the angle of your push. That's all torque is. It's the effective twist.
And this brings us to another beautiful equation, Newton's second law, but for rotation. You know F equals ma, right? Well, get a load of this. Net torque equals rotational inertia times angular acceleration. It's the exact same idea. A bigger twist, or less resistance to spinning, gives you a bigger change in your spin. It's Newton's brilliant insight, just translated perfectly into the world of rotation.
So how do we actually use this stuff on a real problem? This slide shows the classic strategy. Imagine a falling block pulling a cord wrapped around a pulley. You have to analyze it in 2 parts. Step 1, just look at the block. That's a linear problem, so you use F equals ma. Step 2, just look at the spinning pulley. That's a rotational problem, so you use our new friend, torque equals I alpha. The key is step 3. The cord connects them. It's the bridge that lets you relate the 2 systems. You just divide, analyze, and then connect.
Okay, for our final block, we're going to change gears completely. We're going to look at all this spinning stuff from a totally different, but just as powerful point of view, the perspective of work and energy.
We all know that a moving object has kinetic energy, 1/2 mv squared. Well, surprise, surprise, a spinning object has rotational kinetic energy. And just look at the formula, 1/2 I omega squared. It's the same structure all over again. You just swap out mass m for rotational inertia I, and you swap out linear velocity v for angular velocity omega. It's the energy of motion, but for things that are spinning.
And don't ever think this is just some abstract number. This energy is real, and it can be absolutely immense. This picture shows what happened when an industrial spin test went horribly wrong back in 1985. A heavy steel rotor was spinning incredibly fast. When it shattered, all that stored rotational energy was released with an explosive force of 21 million joules. It was powerful enough to blow a massive steel lid clean through a concrete roof. It's a pretty sobering reminder that this stuff isn't just on paper. It's a real and powerful force.
So let's end by just appreciating this last table, from kinetic energy, to work, to power, all the way down to the fundamental work-energy theorem. The parallels are perfect. For every single concept in linear motion, there is a perfect mirror image in rotational motion. It's just a beautiful, symmetric, unified way to understand how things move, whether they're going straight or just spinning in circles.
So, we've built up this whole toolbox for understanding things that only spin. But what about things in the real world that do both at once? Think about a wheel rolling down a hill. It's moving forward, that's translation, and it's spinning, that's rotation. So how do we combine everything we've learned to describe that kind of motion? Well, that's where the next chapter of physics really begins.